In Chapter 3, we're going to start taking a look at these things called matrices and some applications and how we can use matrices to solve problems. So today we're just going to take an introductory look. An introduction to matrices. Kind of what we can do with them and how we can mathematically manipulate them. Now, a matrix is simply a fancy way of saying a rectangular array of numbers. And the way we note a matrix is we put it in these little brackets. And so you'll see some numbers, maybe 3, 1, 4 in the first row, and 7, -3, 0 in the second row. That's a matrix, just a rectangle array of numbers. It's got rows and it's got columns. And in fact, those rows and columns give it what we call the dimensions. The dimensions, we always list the rows first by the number of columns that the matrix has. So, for example, this blue matrix on the screen here has 1, 2 rows and 1, 2, 3 columns. And so we say that blue matrix is a 2 by 3 matrix, meaning it has 2 rows and 3 columns. And basically, our general purpose, just showing a real simple version of a matrix, is the purpose of a matrix is to organize and manipulate large amounts of data. So let's take a really quick example of how we can organize and manipulate some data. We're going to oversimplify it here and say a company sells tablets in Ephrata in Moses Lake and in Soap Lake. Their sales in hundreds are given below. Let's say we've got, I'll do this in green. We've got Ephrata, Moses Lake, and Soap Lake. We're looking at sales in 2012 and 2013. And they sell maybe iPads and the Google Nexus. And so let's say in Ephrata they sold 7 iPads and 4 Nexus in 2012. Moses Lake, there were 11 iPads and 9 Nexus. Soap Lake, there were 4 iPads and 2 Nexus. In 2013, Ephrata had 8 iPads, 7 Nexus. Moses Lake had 14 and 16 Nexus. And Soap Lake 5 and 3. Well, what we can do is we can make a matrix to represent each year in this example. So let's say we make a matrix for 2012. A 2012 matrix will have 2 columns, 3 rows, So it's a 3 by 2, and we'll just put the numbers in here, 7, 4, 11, 9, 4, and 2. And I'm going to call that matrix A for the sake of our example. And for 2013, the numbers would be 8, 7, 14, 16, 5, and 3. That's 2013. And that's going to represent matrix B. So now we've got these two matrices, and we know that the first row is Ephrata, the second row is Moses Lake, the third row is Soap Lake. The first column is your iPads, and the second column is the nexus. We can manipulate this in several ways now. Let's say we want to find the difference in sales. We want to know basically how much has B increased over A. Basically, we're taking matrix B and we're subtracting matrix A. So matrix B would be that 8, 7, 14, 16, 5, 3. And we're going to subtract matrix A, the 7, 4, 11, 9, 4, 2. And now it wouldn't make sense to subtract Ephrata's iPads from Soap Lake's nexus. We want to know the individual entries. And so it just makes sense while we're subtracting these to subtract Ephrata's iPads and Ephrata's iPads. 8 minus 7 is 1. It also makes sense just going across. We're going to subtract Ephrata's nexus from Ephrata's nexus. 7 minus 4 is 3. And we can continue on. 14 minus 11, that's 3 also. 16 minus 9, that's 7. 5 minus 4 is 1. And 3, whoops, didn't change colors. 3 minus 2 is 1. And so we can see the difference now in Ephrata's, Moses Lake, and Soap Lake's iPad and nexus. So we can quickly see in Moses Lake there were 3 more iPads sold. In Soap Lake there was 1 more nexus sold. We can see those values in the table. It's almost like an Excel spreadsheet. We could even do another thing with these. Let's say I wanted to have a goal to double my sales. We're actually going to double the 2013 sales. Actually, I don't want to double. That's too conservative. I'm optimistic. We're going to triple the 2013 sales. Well, what we're really asking to do there is we're going to take the 2013 sales, which was matrix B, and we're going to triple it or multiply it by 3. So we've got 3 times matrix B, which is the 2013, 8, 7, 14, 16, 5, and 3. And it makes sense to say we don't want to just triple the iPad sales. We don't want to just triple Moses Lake sales. We want to triple every single sale. So we've got to do 3 times each entry. 3 times 8 is 24. 3 times 7 is 21. 3 times 14 is 42. 3 times 16 is 30 plus 24, 54. Nope, 48. How about that? 30 plus 18. Yeah. 3 times 5 is 15. And 3 times 3 is 9. And so we can see now in maybe 2020, when we triple our sales, in Ephrata, Moses Lake, and Soap Lake, how many iPads and Nexus need to be sold in order to meet our goal. That's kind of the idea behind matrices, is we organize data, and then we can manipulate that data in order to work with it. I want to clearly identify, though, exactly what we're doing with these matrix operations. Instead of just saying, well, it makes sense that we're going to add this way and multiply this way, I want to clearly identify some matrix operation. So to set this up, we need a couple matrices to play with. So I'm going to say matrix A, a 3 by 3 matrix, 1, 3, negative 2, 4, negative 2, 0, 1, 3, 9. Matrix B, it's going to be a 3 by 2 matrix, 1, 4, negative 3, 0, 2, 5. And matrix C, just for the sake of our example, we're going to make it 4, 2, negative 1, negative 3, 5, 1, 0, 6, negative 2. First thing we're going to do with matrix operations is we are going to either add or subtract them. So to formally define adding and subtracting, we either add or subtract corresponding entries. And here's a little caveat with adding and subtracting is the matrices must be the same size. Because if one matrix has 3 columns and the other one doesn't, what do we add the third column to? Nothing really. So they must be the same size in order to add and subtract. So, moving too fast here. Let's do matrix A plus matrix C. Okay, well, matrix A is 1, 3, negative 2, 4, negative 2, 0, 1, 3, 9, plus matrix C, which is 4, 2, negative 1, negative 3, 5, 1, 0, 6, negative 2. And so if we're just going to add the corresponding entries, that means we take the first entry and add the first entry. 1 plus 4 is 5. Continuing across, 3 plus 2 is 5. Negative 2 and negative 1 is negative 3. 4 and negative 3 is 1. Negative 2 and 5 is 3. 0 and 1 is 1. 1 and 0 is 1. 3 and 6 is 9. 9 and negative 2 is 7. So you can see we added the corresponding entries. We said, whoops, we didn't do that. We said 3 and 2 is 5. 1 and 4 is 5. Negative 2 and negative 1 is negative 3. Adding the corresponding entries. That's how we add. Subtraction we already saw in the previous example, so I'm going to skip subtraction. But how about if I want to do B plus C? Now, matrix B, if you wrote it down in your notes, you'll see that matrix B was 1, 4, negative 3, 0, 2, 5. Matrix C was 4, 2, negative 1, negative 3, 5, 1, 0, 6, negative 2. But we have a problem here. You notice matrix C has a third column. Matrix B does not have a third column. These two matrices are different sizes, and so there is no solution. We can't add them. So very important, to add and subtract matrices, they have to be the same size. The next thing we're going to do with matrices is what is called scalar multiplication. Now, scalar multiplication, what we're going to do is we are going to multiply each entry by the scalar. which is another fancy way of saying a constant, or just a number. This is what we did when we multiplied the matrix for 2013 by 3 to triple it. We multiplied each entry by 3. And it's the same thing we do here. So we don't need much examples here. We've already seen this before. Let's do -4 times matrix B. So we're going to take -4 times matrix B, which was 1, 4, -3, 0, 2, 5. And to do this, we multiply the -4 times each entry. So -4 times 1 is -4. -4 times 4 is -16. -4 times -3 is 12. -4 times 0 is 0. -4 times 2 is -8. And -4 times 5 is -20. And so this is what we get when we scalar multiply each entry by the scalar, or by the constant. Now addition and subtraction are pretty straightforward as operations. We can actually do various combinations of adding and subtracting and scalar multiplication. It's a combination of add and scalar. And when we do a combination, same as always, we think about the order of operations. Now, order of operations tells us that we should multiply before we add. So if I have 3a minus 5c, we're going to do all the multiplication first, and then we will do the addition and subtraction. So we've got 3, get some blue here. We've got 3 times matrix A, and matrix A was 1, 3, -2, 4, -2, 0, 1, 3, 9, minus 5c. And matrix C was 4, 2, -1, -3, 5, 1, 0, 6, 2. I'll give us some white space to work, because this is going to take up some space. So first we do the multiplication. We're going to multiply by the scalar, multiply everything by 3, multiply everything by 5. And when we do, we have to decide, are we going to multiply by -5 and add the result, or are we going to multiply by 5 and subtract the result? I'm just going to multiply by 5. You can multiply by -5 and add if you want. It all comes out the same. So multiplying by 3, we have 3, 9, -6, 12, -6, 0, 3, 9, and 27. Minus, and now we're going to multiply by 5, because I kept the negative. So I'm just multiplying by 5. So 5 times 4 is 20, 10, -5, -15, 25, 5, 0, 30, and 10. And so now we can actually subtract these matrices to get our final solution. Again, doing it unit by unit, 3 minus 20 is -17. 9 minus 10 is -1. -6 minus -5, minus a negative is going to be plus, so that also becomes -1. 12 minus -15 is 27. -6 minus 25 is -31. 0 minus 5 is -5. In the third row, 3 minus 0 is 3. 9 minus 30 is -21. And 27 minus 10 is 17. And so we get our final matrix here, 3a minus 5c. So that's kind of the basic matrix operations, adding, subtracting, and multiplying by a scalar. I want to talk about another operation, which is going to get its own bullet point because we're going to plant here a while. This is an operation that is probably used the most with matrices, and that is multiplication. If my pen will write, multiplication of matrices. This is where we multiply a matrix times a matrix. And this is going to take a little bit more work. First, the how we do it. What we're going to do is we are going to take a row from the first matrix and multiply it by the column of the second matrix. So the row of the first times the column of the second, and then we will add all the products together. It's going to make more sense when I show you an example. We'll do a little color coding to make it clear what we're doing. But the other important rule is if we are multiplying an M by N matrix times an N by P matrix. This is very important. When we multiply the two center values, the columns of the first matrix and the rows of the second matrix must be the same. And then the solution is the dimensions on the outside. M by P. So the inside numbers have to be the same on the dimensions. The outside numbers is the solution. So let's do some examples to really look at this. It feels a little awkward at first just because it's a new process, but once you kind of get the pattern of how we multiply these matrices, it's actually quite straightforward. So it's worth practicing. It is the most used operation. In fact, we're going to use it extensively over the next couple days and even all the way out into the very last unit of this course. So very important we get this. So really basic case, we're going to take a row matrix of 1, -3, 4. So one row, 3 columns, times the column matrix of 5, 1, 0. And now what I want to notice with the dimensions, there is 1 row by 3 columns in the first matrix, and the second matrix has 3 rows by 1 column. Notice the center numbers are the same. The solution is going to be the outside. It's going to be a 1 by 1 matrix for our solution. As we do this, we are going to multiply the row times the column. So as we multiply, the first entry in the first row times the first entry in the first column. That is 1 times 5. Okay? Then we're going to take the second entry and the second entry. That's going to be plus -3 times 1. Then we take the third entry times the third entry. That's going to be 4 times 0. And this is a simple 1 by 1 matrix. There's only one value in here, whatever that adds up to. So we might do a little arithmetic here to simplify it. Might even just do that on our calculator. So on our calculator, 1 times 5 plus -3 times 1 plus 4 times 0, we get the final answer of 8. So notice we multiplied a row times a column. And then we added the individual products together. So let's try one that's a little more involved. It's going to have one row. We're going to multiply 3, -2, 1 by something that has 2 rows and 2 columns. Actually, let's do 3 rows. Sorry, 3 rows and 2 columns. 4, 7, 1, -2, 3, 1. And I'm going to do the dimensions up above here so they don't get in the way later. This first one is a 1 by 3, 1 row, 3 columns. The second one is a 3 by 2, 3 rows, 2 columns. Again, notice the center numbers match. The outside numbers are the dimensions of my solution. My solution is going to have 1 row, 2 columns. It's a 1 by 2 matrix. So first, we've got a 1 row and 2 columns. You can think there's going to be a number there, and there's going to be a number here, right? 1 row, 2 columns. The way we're going to get this is the yellow line you see is in the first row, first column. We're going to multiply the first row times the first column. The blue line you see is in the first row, second column. So we will multiply the first row and the second column. See how that lines up? So actually working it out then, in yellow, first row, first column, we take 3 times 4 plus -2 times 1, working our way across and down, plus 1 times 3. That is in the first row, first column, so we multiplied the first row, first column. Now, the next value is the first row, second column. That's the blue line. So we've got 3 times, this time in the second column, 7, plus -2 times -2, plus 1 times 1. And so you notice that in the first row, second column, we multiplied the first row and the second column. So to get the actual 1 by 2 matrix solution, we're going to multiply these out. 3 times 4 plus -2 times 1 plus 1 times 3 is 13. And for the second number, 3 times 7 plus -2 times -2 plus 1 times 1 is 26. And so our product from multiplying both of these together was 1326. Let's try one that's a little more involved. Multiplying rows times columns. Let's do 135, 246. Times the matrix 5, 4, 3, 2, 1, 0. Now you'll see this first one, first matrix, has 2 rows, 3 columns. The second matrix has 3 rows, 2 columns. The middle numbers match. Our solution is going to be a 2 by 2 matrix. So if we can, just for the sake of envisioning it, it's going to be a 2 by 2 matrix. There'll be something top left, something top right, something bottom left, and something bottom right. And the way we decide what goes in each place is we take the corresponding row and column. So yellow in the top left, that's first row, first column. We're going to multiply the first row times the first column to get the yellow value. In blue, to get that value, it's in the first row, second column. So we're going to multiply the first row times the second column. In green, you see we're in the second row, first column. So we will multiply the second row and the first column together. In purple, we're in the second row, second column. So we're going to multiply the second row and the second column to find out what goes in that spot. So, walking through that, actually plugging in numbers here, clearing out. We're going to need a little bit of space to work so that we can do all that multiplying and adding. So in yellow, first row, first column, we're going to multiply the first row times the first column. So that's going to be 1 times 5 plus 3 times 3 plus 5 times 1. That is the first row, first column. Next, just to its right, it's in the first row, second column, so we are going to multiply the first row times the second column. So in that case, it's going to be 1 times 4 plus 3 times 2 plus 5 times 0. And that is the first row, second column. Now in green. Now we're on the second row, first column. So multiplying the second row times the first column, 2 times 5 plus 4 times 3 plus 6 times 1. That's the first row, second column. Finally, we've got the second row, second column. So in this case, it's going to be 2 times 4 plus 4 times 2 plus 6 times 0. And that's the second row, second column. And now we just have to evaluate each of these to get our 2 by 2 solution matrix. So in the top left, 5 plus 9 plus 5 is 19. On the top right, 1 plus 6 plus 0 is, 4 plus 6 plus 0 is 10. Then we have bottom left, 10 plus 12 plus 6 after multiplying is 28. And finally, 8 plus 0 is 16. And now we've got our product matrix. Multiplying row by column, row by column. And once you get that pattern down, practicing a bit, takes a few steps, but it's quite an easy process. But you got to get that pattern, row times column, row times column. Let's try this one. Let's multiply 4, 1, negative 3, 5 by the matrix 1, 6, 9, 3, 5, negative 4. Checking our dimensions, the first one is a 2 by 2 matrix, 2 rows, 2 columns. The second matrix is a 3 by 2 matrix, 3 rows, 2 columns. Notice the middle numbers do not match. We cannot multiply these matrices together because those middle numbers don't match. The dimensions aren't going to work out because when we try and multiply even the first row, first column together, something's going to happen. We're going to have 4 times 1 plus 1 times 9 plus we're missing a value to be multiplied by the 5. It won't work. We have to be able to get all those corresponding rows and columns together for this definition of multiplication to work. So in this case, we say we cannot multiply them because those middle numbers do not match each other. Let's try another example, kind of give you a preview of what's to come. Let's multiply 5, negative 2, 3, 1 times the matrix x, y. Variables in there. Same exact pattern. We have a 2 by 2 matrix first, 2 rows, 2 columns, and a 2 by 1 matrix second, 2 rows, 1 column. The middle numbers match, so it's going to give us, in outside numbers, 2 by 1 matrix. So there's going to be 2 rows and 1 column. 2 rows and 1 column. The first entry is first row, first column. So we're going to multiply the first row times the first column. 5 times x minus 2 times y. The second entry comes from the second row and the second column. That's 3 times x, if I can get my pen working, plus 1 times y. Now what I want to notice is interesting about this matrix is that looks like a system of equations that we solved back in chapter 1. We would have equations like 5x minus 2y equals a number, and 3x plus y equals a number. In fact, this is one of the biggest uses of matrices that we are going to see. Backing all the way up to major point D, we can look at a system of equations as matrices. We're going to play with this in more detail in future sections, but for now we're going to think about it as now we'll have a matrix A times a variable matrix equals matrix B, the solution matrix. Now matrix A we'll think about as the coefficients. Matrix. All the numbers that are in front of the variables, those are the coefficients. Times, just like in example E above, the variable matrix, where all the variables are listed. Equals this guy, which we're going to call the solution matrix. And the solution matrix is going to just be one column that lists the solutions of the system. So for example, if I have 2x plus 3y minus 5z equals 4, 5x minus 2y plus 3z equals 7, and 4x minus y equals 0, we can represent this system of equations as a matrix multiplication problem. First, we'll have the matrix that represents all of the coefficients. Coefficients, those are those numbers in front of the variables. Notice there's nothing at the last z. We'll get to that in a minute. So the coefficient matrix, all the numbers in front are 2, 3, negative 5. Next row, 5, negative 2, 3. Next row, 4, negative 1 in front of the y. And since there's no value for the z, we still need a number in there. 0 means there's nothing there. And we're going to multiply that by a column matrix, a matrix that's just one column that lists the variables. And you'll see the variables are x, y, and z in order. We want to multiply by that order, x, y, z, x, y, z. And so that's what we'll fill it in with, x, y, and z. And that's going to equal the solution matrix, which represents the solutions of the problem 4, 7, 0. And again, the reason this works is if we were to actually multiply out these matrices, if I multiply the first row times the first column, it's going to give us the first row, first column location. Notice that would be 2x plus 3y minus 5z equals 4. That's that first equation. If I multiplied, again, second row, first column, it'll give me the second row, first column. 5x minus 2y plus 3z equals 7. That's the second equation. And finally, if I multiply the third row times the first column, it'll give me the third row, first column. 4x minus 1y plus 0z, that's just 0, equals 0. And notice that gives me back the original system of equations. So any system of linear equations can be written as a matrix problem. In fact, as you might expect, writing it as a matrix problem will make it easier to solve. But that's the discussion of our next lesson. For now, I want you to take a look at the homework assignment and get really good at working with these operations of matrices, adding them, multiplying by a scalar, and really important to be good at multiplication of matrices, multiplying a row times a column, row times a column. Take a look at the assignment, come to class with questions, and we'll discuss it then.